Swayam Prabha. Digital India. Educated India.
Hi everyone, welcome again to the structural biology course. As you all now know, we are going through high resolution structural biology techniques, and now we are in the module of nuclear magnetic resonance spectroscopy. In the last class, I talked about the magnetism, resonance, and more importantly about the different components of the hardware. In this new class, I will discuss about different small precautions and methodologies we have to take to perform experimentally the NMR spectroscopy experiments. So, let us start with that, and then we will talk about chemical shift. We will talk about some spectra and what are the reason of the spectra to giving different signal in response to one nuclei which is proton. So, let us start with NMR sample preparation. So, first what it need is NMR sample holder, which is actually a NMR tube. So, NMR tube is a thin glass wall tube used to contain sample in nuclear magnetic resonance spectroscopy. If you see in the picture, you see these tubes and caps. Typically, NMR tubes come in 5 millimeter diameter, but 10 millimeter and 3 millimeter sample holders are also known. It is important that the tubes are uniformly thick and well balanced to ensure that NMR tubes spin at a regular rate. For example, they do not wobble, usually about 20 hertz in the NMR spectrometer. So, if you see the solid state sample rotors, these are solution NMR sample tube spinners and NMR sample tubes with caps. So, how we prepare this? The tubes, NMR tubes are a standard length 7 and 9 inch. When chipped and reduced in length, they should not be reused, as an unbalanced tube will not spin properly. So, this is a precaution. We have to clean the tubes thoroughly after use. Cleaning is very important. If you do not clean properly, you will get mixing and different other side effects could be observed. To clean, you should first use the solvent you were using to recover your previous sample. Then you have to rinse several times with acetone and finally dry the sample tube, laying flat on a layer of chemwipe, which we have in the laboratory mostly, or place upside down on a chemwipe in a beaker or Erlenmeyer flask, which we used to use. Choose the container so the tubes stand vertically. Do not heat the tube above 50 degree centigrade, as that could make harm to the glass. Always store unused clean tubes uncapped and laying on a flat surface. For the caps, because the tubes are not cheap, so you could not make it use and throw, but caps are cheap. So, tube caps are disposable and replacements can be easily obtained in a bags of 100. Degassing is a very important part of sample preparation. the NMR spectra recorded using degassed solvent usually benefit from the reduced half height line width and thus better sample to noise ratio. As you know, oxygen gas is paramagnetic, so it might influence. There are several ways of degassing. One is fridge pump thaw technique, that is considered as the best one. Then placing the sample in a ultrasonic bath which works moderately well, or bubbling nitrogen through or over the sample, that is the worst one among the three techniques. What quantity you are going to use for making samples? So, that is very critical. For proton NMR spectra of small organic compounds up to molecular weight 500 Dalton, anything between 1 to 20 milligram of sample would be fine. Concentrated solution can be viscous and that may result in broad signals. Very dilute sample could be masked by impurities and solvent peaks. Carbon 13 is present at approximately 1.1%. We already discussed about the natural abundance. Carbon 12 is the most abundant and carbon 13 is very less abundant. So, when you are using carbon 13, you know that it is intrinsically less sensitive than protons. We could say approximately 6,000 times. So, you have to provide as much sample as possible, 50 to 100 milligram or even more is fine. But when we say that we talked about proton, we talked about carbon 13, preparing two sample, one dilute sample for proton NMR and one concentrated sample for carbon NMR is useful, but it will unnecessarily increase your amount of work. So, it is always good to choose in between a moderately high concentrated solution which does not affect the proton, but also is good enough to collect C13. Solvent height should be uniform, 5 centimeter or 2 inches, which is equal to 0.5 ml. The ends of the sample distort the field homogeneity. Seaming on each sample correct this effect and takes just a minute or so. So, what is seaming? We are going to check. However, vastly different solvent heights prevent complete correction and require many minutes seaming to achieve acceptable homogeneity. Samples prepared with too much solvent waste both time and money and provide poorer signal to noise ratio. However, if you have limited amount of sample which is let us say less than 1 milligram, using less solvent is permissible. Minimum height 1 centimeter, however, this requires special positioning of the sample tube and very intensive seaming, otherwise errors could be happened. So, what is seaming? A seam is a device used to adjust the homogeneity of the magnetic field. Seaming is a process that is carried out to correct any non-homogeneities in the applied magnetic field during a nuclear magnetic resonance experiment. In modern NMR spectrometers, seaming is done using small electrical circuits having some resistance. When current flows in a wire, a magnetic field is generated. So, using these seaming circuits means small magnetic fields can be generated and used to adjust the main applied field and increase its homogeneity. The seaming coils can be in the probe, as it is the field at the sample that needs to be smooth. The coil can adjust the magnetic field in several directions. Typically, an analyst will have to adjust the field in 3 dimensions while measuring the reference peak. So, sample preparation, this is a tube. You have to use clean plus dry NMR tubes and caps. Tubes can be reused, caps should not, as I told earlier. 0.5 ml deuterated solvent CDC3, C6D6, acetone D6 etc. are the common solvent. Substrate requirement for routine spectra 10 mg for proton NMR, 100 mg for carbon 13 NMR. Minimum filling height of tube 2 inches, which is 5 centimeter. Cleaning of tubes, rinse with solvent you are using, rinse with acetone many times, dry in vacuum oven at low temperature less than 50 degrees, because if you do more than 50 degrees, yes, you get more drying, but it could affect the glass property, which will affect your further experiment. So, in sample preparation, what are good solution if we check? This is a clean and clear solution. This is a solution with suspension or the things are opaque. This is a tube with precipitate. This is a tube where we see the development of a concentration gradient. This is a tube where we see a phase developed, like there is phase separation, two phases are there. This is a tube where we see the solvent is not enough. So, this clean clear solution is always good for sample preparation, and all those suspension solution, precipitate, concentration gradient, phase separated and less solvent are considered as bad samples. Simming, I talked about. What simming do? Improves the magnetic field homogeneity. So, if the magnetic field is not uniform within the sample, molecules in different position will experience different field strength, and that means there would be a development of non-homogeneity, which will produce broad, distorted or additional signals. So, to correct this you need to do simming. Coming to good and bad NMR spectra. So, the good and bad NMR spectra are the result of homogeneity of magnetic field, as we have discussed earlier, how you prepare your sample, because if some body is not taking care properly in washing, cleaning and all, if you are reusing caps and all, so that all are coming into sample preparation. Proper sample preparation is a very critical thing for getting good NMR spectra. Choice of solvent we have already talked about. There are standard solvents, you should use them so that the sample is soluble. Data acquisition parameters, what are the parameters you are using for data acquisition, and processing procedures, how the acquired data is processed. So, NMR spectrum, what is a NMR spectrum? NMR spectra or NMR spectrum is the graphical representation of NMR signal, which is analyzed towards understanding the molecular level information. The spectrums are unique, well resolved, analytically tractable and often highly predictable for small molecules. So, the small molecule, if you think they have only few carbon, let us say methyl bromide. In these all the 3 hydrogens are same. So, it is very predictable. But in case of that, if you have a protein molecule where there are different hydrogens which are in different environment, it is not straightforward. Different functional groups are obviously distinguishable, and identical functional groups with differing neighboring substituents still give distinguishable signals. NMR has largely replaced traditional wet chemistry tests such as color reagents or typical chromatography for identification. A disadvantage is that a relatively large amount 2 to 50 milligram of purified substance is required, although it may be recovered through a workup. As we say, it is a non-destructive technique. Proper procedures are required to obtain the NMR spectra, and depending on several factors, spectra could be good or bad. So, a good spectrum, what are the criteria? The criteria is there would be presence of integrals in the assigned value, and we could easily get the picking. So, if that is the criteria of a good spectra, we would also try to understand what is a bad spectra. So, in a bad spectra, if you see this is a bad spectra, no unit specified for axis as well as picking. This axis picking. The signal to noise, the S by N ratio is bad. So, that is why these are criteria of bad spectrum. Then if you see the spectrum is so big that it already cut down, tall signals they are cut off, it is not an example of a good spectrum. Signals being too small, only allowed when trying to compare signal intensities between different spectra, otherwise it is not allowed, and this is also an example to come under bad spectrum. Broad signals also are not good. Signals are distorted, so automatic phase correction is often insufficient. We have to take care of that. So, that are also example of bad spectrum. And excessive picking, probably because of when you see here low PP threshold, also due to improper phasing. Existence of areas without signals, which it should be excluded, an example of bad spectrum. If you want to print all your spectra with a default range 0 to 10 ppm, do not forget to print detail expansion. So, these are few example of bad spectrum. Now, we will talk about the nature of NMR absorptions, because that would help us understanding how the spectras are coming. The absorption frequency is not the same for all 1H, which is proton, and 13C nuclei. Nuclei in molecules are surrounded by electrons, as we know. So, when we say hydrogen, it is surrounded by 1 electron, when it is carbon, it is surrounded by 6 electrons. Electrons set up tiny local magnetic fields that act in opposition to the applied field, shielding the nucleus from the full effect of the external magnetic field. So, we talk about the magnet developed by the nucleons. Now, we also know that the electrons set up tiny local magnetic fields, and they act in the opposition to the applied field. So, they shield the nucleus from the full effect of the external magnetic field. That means, more number of electron, more shielding. A carbon is shielded more than the proton. The effective field actually felt by the nucleus is the applied field reduced by the local shielding effect. So, B effective equal to B applied minus B local. Each chemically distinct nucleus in a molecule has a slightly different electronic environment and consequently a different effective field. Each chemically distinct 13C or 1H nucleus in a molecule experiences a different effective field and will exhibit a distinct 13C or 1H NMR signal. In nuclear magnetic resonance spectroscopy, the chemical shift is the resonant frequency of a nucleus relative to a standard in a magnetic field. Often the position and number of chemical shifts are diagnostic of the structure of the molecule. Chemical shifts are also used to describe signals in other forms of spectroscopy such as photoemission spectroscopy. So, what is chemical shift? Some atomic nuclei possesses a magnetic moment or nuclear spin which give rise to different energy levels and resonance frequency in a magnetic field. The total magnetic field experienced by a nucleus includes local magnetic fields induced by currents of electrons in the molecular orbitals. Now, you could think that the electrons have a magnetic moment themselves, which we talk about. The electron distribution of the same type of nucleus 1H, 13C, 15N usually varies according to the local geometry like binding patterns, bond lengths, angles between bonds and so on, and with it the local magnetic field at each nucleus. This is reflected in the spin energy levels and resonance frequencies. The variation of nuclear magnetic resonance frequencies of same kind of nucleus due to variation in the electron distribution is called chemical shift. The size of the chemical shift is given with respect to a reference frequency or reference sample, usually a molecule with a barely distorted electron distribution. So, chemical shift is the frequency of the signal minus frequency of the reference divided by the spectrometer frequency into 10 to the power 6, that is chemical shift or delta. An NMR spectrum is a plot of the radio frequency applied against absorption, as we talked about. A signal in the spectrum is referred to as a resonance, we discussed that too. The frequency of a signal is known as its chemical shift or delta. The chemical shift in absolute term is defined by the frequency of the resonance expressed with the reference to a standard compound which is defined to be at 0 ppm. So, you need to have a compound which is kind of NMR inactive. So, that would work as a reference which is 0 ppm. The scale is made more manageable by expressing it in parts per million or ppm and is independent of spectrometer frequency. Otherwise, if it would be dependent on, then it would be more complex even. The operating frequency omega 0 of a magnet is calculated from the Larmor equation. Omega 0 is gamma B 0, where gamma is the gyromagnetic ratio and B 0 is the applied magnetic field. What is Larmor frequency? In physics, Larmor precision, which is named after Joseph Larmor, is the precision of the magnetic moment of an object about an external magnetic field, where B 0 is the actual strength of the magnet in units like Teslas or Gauss, and gamma is the gyromagnetic ratio of the nucleus being tested, which is in turn calculated from its magnetic moment mu and spin number I with the nuclear magneton mu n and the Planck constant h. So, gamma is mu n by h I. So, for example, the proton operating frequency for 1 Tesla magnet is calculated as omega 0 equal to gamma B 0 equal to the values 2.79 into 5.05 into 10 to the power minus 7 J by T divided by 6.62 into 10 to the power minus 34 J's into half into 1 T equal to 42.5 megahertz. So, the MRI scanners are often referred to by their field strength B 0, whereas NMR spectrometers are commonly referred to by the corresponding proton Larmor frequency. For example, a 300 megahertz spectrometer which has a B 0 of 7 Tesla. While the chemical shift is reference in order that the units are equivalent across different field strengths, the actual frequency separation in Hertz scale with field strength B 0. As a result, the difference of chemical shift between two signals present a larger number of hertz on machines that have larger B0, and therefore, the signals are less likely to be overlapping in the resulting spectrum, they are more separated. This increased resolution is a significant advantage of analysis. Larger field machines are also favored on account of having intrinsically higher signal arising from the Boltzmann distribution of magnetic spin state. So, this is one, but the other one is larger field machine, more powerful machines. Coming back to chemical shift, the chemical shift delta is usually expressed in parts per million by frequency, because it is calculated from, as I talked about, new sample by new reference divided by new reference, where new sample is the absolute resonance frequency of the sample and new reference is the absolute resonance frequency of a standard reference compound measured in the same applied magnetic field B0. Since the numerator is usually expressed in hertz, then the denominator is megahertz, delta is expressed in ppm. The detected frequency in hertz for proton, 13 carbon and 29 silicon nuclei are usually referenced against TMS, tetramethylsilane, TSP, tetramethylsilyl propanoic acid, or DSS, which by the definition above have a chemical shift of 0 if chosen as the reference. So, TMS, TSP and DSS are chosen as reference because their value of 0 ppm. Other standard materials are used for setting the chemical shift for other nuclei. Thus, an NMR signal observed at a frequency 300 hertz higher than the signal from TMS, where the TMS resonance frequency is 300 megahertz, has a chemical shift of 300 hertz divided by 300 into 10 to the power 6 hertz equal to 1 into 10 to the power 6, which is 1 ppm. Although the absolute resonance frequency depends on the applied magnetic field, the chemical shift is independent of external magnetic field strength. So, applied magnetic field is required, because without the applied magnetic field the NMR experiment is not possible, the orientation, the alignment is not possible, but the value of the chemical shift is independent of the external applied field. So, that means the chemical shift or delta value is independent of machine. On the other hand, the resolution of NMR will increase with applied magnetic field. So, the electrons around a nucleus will circulate in a magnetic field and create a secondary induced magnetic field. This field opposes the applied field as stipulated by Lenz's law, and atoms with higher induced fields are therefore called shielded relative to those with lower electron density, as you could compare between proton and 13C. The chemical milieu of an atom can influence its electron density through a polar effect. So, we are talking about first just the nuclei, a proton and a 13C, but now we are going to molecule, like if we have now here there are 3 type of hydrogens. So, for example, electron donating alkyl groups, we will talk about this also in details. Electron donating alkyl groups, for example, lead to increased shielding, while electron withdrawing substituents such as a nitro group lead to deshielding of the nucleus. Not only substituent cause local induced field, bonding electrons can also lead to shielding and desilting effects. Coming to the induced magnetic field, a striking example of this is pi bond in benzene. Circular current through the hyperconjugated system causes a shielding effect at the molecule center and a desilting effect at its edges. So, both the effect. Trends in chemical shifts are explained based on the degree of shielding or desilting. Nuclei are found to resonate in a wide range to the left or more rare to the right of the internal standard when a signal is found with a higher chemical shift. The applied effective magnetic field is lower if the resonance frequency is fixed, as in old traditional CW spectrometers. The frequency is higher when the applied magnetic field is static, which is a normal case in Fourier transform spectrometers. The nucleus is more desilted, the signal or shift is downfield or at low field or paramagnetic. Conversely, a lower chemical shift is called a diamagnetic shift and is upfield and more shielded. Coming to another factor which is called magnetic anisotropy. The word anisotropy means non-uniform. So, magnetic anisotropy means that there is a non-uniform magnetic field. The electrons in the pi system, which we are discussing in the last slide, aromatics, alkenes, alkynes, carbonyls. So, aromatics definitely have a conjugated system, alkenes, alkynes, carbonyls also have pi electronic system, interact with the applied field which induces a magnetic field that causes the anisotropy. As a result, the nearby protons will experience three fields: the applied field, the shielding field of the valence electrons and the field due to the pi electronic system. Depending on the position of the proton in this third field, it can be either shielded or deshielded, which implies that the energy required for and the frequency of the absorption will change. You will see that in the aromatic you have the conjugated pi system. So, you have three factors: field line oppose the applied field, creating a reduced field in this region is one, anisotropic induced magnetic field lines due to the induced circulation of the pi electrons in benzene, and field lines which aligned with the applied field, creating a larger field in this region. So, if you look at them, you will see that how the delta values are changing. Schematic diagram of shielding cones to common pi system. So, this is benzene system, the chemical shift, the value is 7 to 8 ppm. When it is a alkene system, it is 5, delta is 5 to 7, a double bond. Then a carbonyl, their delta is 9 to 10 and a triple bond between carbon, here delta is 2 to 3 ppm. It is often convenient to describe the relative positions of the resonances in an NMR spectrum. For example, a peak at a chemical shift delta of 10 ppm is said to be downfield or deshielded with respect to a peak at 5 ppm. So, what we mean here, it should be relative, like when it is 10 ppm in respect to 5 ppm it is deshielded, whereas the peak at 5 ppm is upfilled or shielded with respect to the peak at 10 ppm. It is relative. Typically, for a field strength of 4.7 Tesla, the resonance frequency of a proton will occur around 20 megahertz and for a carbon around 50.4 megahertz. The reference compound is same for both tetramethylsilane or TMS. H atom is the one which have helped popularizing the use of NMR spectroscopy. We have talked several times. If you take any compound, you see the presence of a proton, and more importantly proton, the one H also have a population of 90%, making the signal stronger. But can you imagine that there are different types of hydrogen? Yes, there are different type of hydrogens with respect to the NMR technology, because if, as you already have started understanding, proton is used everywhere in NMR, but then if proton is everywhere, how you get the signals differentiated? It is differentiated because NMR could have separate the proton peaks. So, they consider different type of hydrogens. What do you mean by different type of hydrogens? So, first let us go for a terminology which might seem to be a trivial concept, but the idea of establishing the number of kinds of hydrogen is a very important useful concept, especially in NMR. Especially in NMR spectroscopy, where for example, different type of hydrogen or other atom typically each give rise to a different signal. The idea is developed below, like where we are going in the next slide for hydrogen atom, but can be extended to any type of atom, but because of its omnipresence we are more interested in hydrogen. So, a hydrogen atom is different to another hydrogen atom if it is not in an identical environment. When we say environment, we say chemical environment. Like if you think about, we will talk, if you see these three hydrogen atoms are in similar environment, whereas these three hydrogen are in different to this hydrogen which is in a different environment. So, that is what we are going to investigate. This could mean it is attached to a different type of atoms. Compare CH versus OH, it is connected to carbon or it is connected to oxygen, or it is connected to a double bonded carbon and single bonded carbon, triple bonded carbon, or due to the number of adjacent hydrogen like 3 hydrogen, or just at different point in a chain. We will discuss different type of scenarios here. So, counting the number of different kinds of hydrogen. There are 3 methods that can be used to count the number of kinds of hydrogen. Each achieve the same result. You will probably find it best to master the first of this method because it is more easy, which we are going to discuss, and over time you will find yourself moving towards the third method. The first method is called substitution method. As I told, it is the simplest one. The idea is that you replace each hydrogen in a molecule in turn with a dummy atom, for example, a chlorine, to see if you get a different product. For example, one that will require a different name, the different position. Each new product indicate a different type of hydrogen. This idea is related to the radical chlorination of alkanes, where sum of each possible product is usually obtained. For example, if you remove one hydrogen from chloroethane and substitute it for another chlorine atom, how many different molecule can you make? 2 products, 1 dichloroethane and 2 dichloroethane. Hence, there are 2 type of hydrogen in chloroethane. Okay. So, in that way you have to do the substitution. So, you get chloroethane and you substitute 1 hydrogen with chlorine and you see how many compounds you are making. Verbal description. The verbal method requires that you describe the position of each hydrogen within the molecule. If you need to use different words to describe 2 hydrogen atoms, then they represent different type of hydrogen. For example, an OH is different to a CH based on what they are attached to. A CH3 is different to a CH2 because the number of hydrogen at each carbon are different. sp3 carbon hydrogen is different to an sp2 or sp carbon hydrogen. Other differences could be position on a chain, across a ring or double bond, etc. So, you look at them, you start naming. If there is a different name, this is a different hydrogen. Symmetry. The symmetry method is the most sophisticated, but the quickest method and requires that you look for the mirror planes, rotation axis or inversion centers that interchange hydrogen atoms. Because you are coming from crystallography, so we talk about all of this, we talk about mirror planes, we talk about rotation axis, we talk about inversion in the symmetry. So, the hydrogen atoms that can be interchanged by symmetry are equivalent to each other. So, here is the terminology. There are majorly three types: homotopic, enantiotopic and diastereotopic. Homotopic is replacement of the group give the same product. For example, it does not matter which of the hydrogen atoms in bromomethane is replaced with chlorine, we always get bromochloromethane. Hence, these three hydrogens are said to be homotopic. Homotopic hydrogen always gives the same NMR signal. Enantiotopic, replacement of the groups gives enantiomer. Consider the hydrogen atom in a methylene group in bromoethane. If we replace one of those hydrogen with a chlorine, we create a chirality center, because then there is a difference. Therefore, depending on which of the two hydrogen is replaced, we get one enantiomer or the other. Okay. Hence, these two hydrogens are said to be enantiotopic. Enantiotopic hydrogen give the same NMR signal in an achiral environment, which is the normal NMR condition. Diastereotopic, consider the hydrogen atom in a methylene group in 1-bromo 1-chloropropane. Now, there is already a chirality center at C1. If we replace one of those hydrogen with a chlorine, we create a new chirality center. Therefore, depending on which of the two hydrogen is replaced, we get one diastereomer or the other. Hence, these two hydrogen are said to be diastereotopic. Diastereotopic hydrogen are different, and in principle they give rise to different signals, and hence they can couple to each other. So, there are three types in terms of terminology: homotopic, enantiotopic and diastereotopic. Now, we are going to the spectra and we are looking at what we call integration. Integration is a mathematical term that means the area under a curve. In NMR, the curve is the spectra and the integration is a measure of the area of the peaks in the spectra. The key thing here is that the area of the peak is proportional to the number of atoms that it represents. So, in an HNMR, the integration of a peak gives the area of the peak, and this area gives us a measure of the number of hydrogen atom it represents, the number of hydrogen of that type. In many modern NMR spectra, the peaks on the spectra often look to be lines rather than peaks, and this tends to lead to students thinking about peak height rather than area, but it is actually the area which is important. So, how do we measure the integration? Here, to measure the area of the integration, there are two methods which are principally used. We should point out that the area is measured by the spectrometer itself and plotted on the spectra. We are talking about what we need to do to interpret that information. So, number on spectra method. The numbers are typically printed under the peak, often with a bar or two marks that represent the limits of the integration. For example, the x axis start and ends points for the area measurement. The limits are set by the person processing the spectrum. In the example here, the green bar is shows the limit and the area is 3. Steps on integration curve, which is traditional. Older instrumentation used to plot a second curve in the example to the right in blue above the actual spectra, where the integration was recorded as a series of steps. The height, which is represented by the arrow in the furthest right image here, of this step needs to be measured with a ruler and record, and then compared to the other steps in the same spectrum to get the relative ratio. So, that is steps on integration curve. So, what we do using integration information? Integration can only tell you the relative ratio of the number of hydrogen of each type. For example, you cannot get a useful integral if there is only one type of hydrogen. The sum of the integrals represent the empirical number of hydrogen and can it related to the molecular formula. So, the integral sum into an integer equal to the number of hydrogen in the molecular formula. The number of aromatic hydrogen on a benzene ring or vinyl hydrogen on an alkene can establish the number of substituents present. What are the limitations of integration method? Under normal condition, the accuracy is likely close to 5%. This can be improved if required by modifying the experimental condition. Overlapping peaks make the situation more difficult, but a total area of the overlapping peaks should be possible to measure. Exchangeable hydrogen often integrate low. This can be improved if required by modifying the experimental condition. Exchangeable hydrogen means in hydroxide it could be in two state and O minus. So, here hydrogen is present, here hydrogen is absent. Integral accuracy is affected by sample quality and processing. So, it is important to pay attention to this factor also. NMR chemical shifts. The chemical shift is the position of the delta scale where the peak occurs. Typical delta or ppm values for protons in different chemical environments are different, as we told, and if you look at here, the chemical shifts for protons are shown which is being influenced by a single group. So, if you see the methyl, methylene and all this carbon with single bond, they come around 0 to 1 more towards 1. Then when there are nitrogen, sulfur and all, they come under 2 to 3. Then with oxygen and other negative group they come around 4. Then with double bond they come between 5 to 6. Then aromatic hydrogen comes in 7. Then with carbonyl it come between 9 and 10. Then the OH group in a carboxylic group it comes around 11. In cases where a proton is influenced by more than one group, the effects are essentially cumulative. We talked about those compounds and their effects. So, let us discuss with them. So, let us take methyl bromide. So, this is methyl bromide, this is bromine and this is carbon and this is 3 hydrogen making this methyl. So, there are 3 hydrogens and all of them are equivalent because they only have, they are connected to carbon and the effect of bromine is same on them. So, as the methyl bromide contains only one type of hydrogen atoms, only a single peak is observed and that peak is at 2.7. So, this is the standard at 0 TMS working as a 0 standard like standard molecule. So, if you remember with carbon to hydrogen they are between 1 to 2 because of the presence of the bromine which is having electron withdrawing effect, it is negatively charged. So, it draws the electron, have less shielding effect, we see the shift from here to higher values. There occurs a slight deshielding due to the presence of bromine as I told. No integral because integration provide the relative number of each type and here there is only one type as again we discussed. Coming to the spectra of acetone. Acetone is CH3 CO CH3, 2 CH3 and a double bonded oxygen. So, this is acetone. Acetone also contains only one type of hydrogen atom only. So, if you see there are 6 hydrogens and all of the 6 hydrogens if you separate they are connected to carbon and all of them are connected to one oxygen. So, the value comes at 2.2, this value is 2.2. There occurs a very minute deshielding due to the proximity of carbonyl group. So, if you think this is CH3 CO CH3. So, the carbon, the oxygen is now taking the electron, but this deshielding is divided between 6 of them. So, you get minor. If you remember when we are talking about bromine which is more electronegative in terms of its power, it was working on. So, when I say bromine is more electronegative, what I mean is it have a direct effect. This oxygen does not have a direct effect. This is affecting on this carbon and then that is why there is a deshielding, but there is a direct deshielding and also there is only 3. So, if you go back you will see that this was having a value of 2.7. So, in comparison to 2.2 there is a shifting 2.7 for this compound. Again no integral because integration provides the relative number of each type and here there is only one type. Now, we are talking about CH3COOCH3 which is methyl ethanoate. So, to make this I have to integrate a oxygen here. So, now if you see this is methyl ethanoate, what you have is CH3 CO OCH3. So, here in methyl ethanoate you have a extra oxygen which is first of all differentiating between this CH3 and this CH3, because you have two different type of hydrogen. Now, you have 2 peaks. So, methyl ethanoate contains 2 type of hydrogen atom, hence 2 peaks are observed in the spectra, one at 2.1, mostly the same we got in the last one and other at 3.7. The peak at 3.7 ppm is because of the OCH3 group. So, if you look at this is because of the OCH3 group, because here it is directly taking. So, the peak at 3.7 ppm is because of the presence of the OCH3 group, because the presence of the electronegative oxygen which desilts the methyl group. The integration are 1:1, as in both case 3 hydrogens are present. So, you see mostly same size of peak. Now, coming to tertiary butyl bromide. Again there is a bromide, there is a bromine, but all 3 methyls are there. So, there are 9 hydrogens and all of them are equal. As tertiary butyl bromide contains only one type of hydrogen atom, only a single peak is observed at 1.8. So, if you remember when it was CH3Br, here whatever it is taking, it is distributed. The desilting is distributed. Here it was not distributed, and that is why the peak shifted. Since the bromine atom is further away from the hydrogen atoms than methyl bromide, desilting is relatively less than methyl bromide. No integral, because integration provides the relative number of each type, and here also we have only one. The last one is coupling, where we have 1,1 dichloroethane. So, it is methyl group, carbon and 2 chlorine, CH3 CH Cl2. Okay. So, here the compound, 2 type of hydrogen. So, 2 peak, the compound contain 2 type of hydrogen atom. So, a doubly peak is observed, one at 2.1 ppm for this and a quartet at 5.9. So, first of all, why this we know, right? Methyl group 3 hydrogen, more intense peak. This quartet is because of this, right? Why? So far the H NMR spectra that we have looked at have all had different type of protons that are seen as singlets in the spectra. We see singlets, but here we see a quartet and a doublet here. This is not the normal case. The spectra usually have peaks that appear as groups of peaks due to coupling with neighboring protons. So, what is happening here is the electron withdrawing plus the coupling effect. If you look at here, we have the splitting. Why we have the splitting? We have because if you see in this, you have positive inductive effect, electron withdrawing effect of 2 chlorine, and what we were thinking about on bond, this is because of the coupling with neighboring protons. So, we know about chemical shift. Up to now we are looking at their effect, but we did not see what is coupling, right, due to neighboring the presence of neighboring protons. In the next class, we will talk about the effects we have observed here, the coupling and many more, and then we will see the effect there, and up to now whatever we are studying in 1D spectra, proton spectra. In the next class we will talk about different spectra together, a proton spectra, a carbon spectra in one graph, that is called 2D spectra, a proton, carbon and nitrogen spectra in one graph, which is a 3D spectra. So, these will be complicated, but this will show how powerful NMR is in deducting the informations. So, in this class we talk about sample preparation, good and bad spectrum, chemical shift and different type of protons and the effect of chemical shift in the plotted spectrum. We are ending with a concept of coupling, which we try to see, but we will go in details in the next class. Thank you very much.